Okay, so we're gonna begin with a motivation. First of all, let's define what Fourier analysis is. Um, so Fourier analysis, it's basically, if you want to say it roughly speaking, it's the study of, let's say, ways of representing functions with specific properties like periodicity, which is something that we're going to talk about, in terms of, let's say, representing or approximating functions in terms of sums of simpler functions. Okay, this is a little bit vague. What does that mean? Well, before we get deeper into this stuff, let's agree on some terminology that we will be using throughout the course. So let's just make some conventions here. Recall that functions like cosine, let's say cosine 2 pi and x, and sine 2 pi and x, these functions, they have the property that, as you see in the figure in front of you, for example, cosine 2 pi x, it's periodic in the sense that it repeats itself. So we're gonna define things formally, but let's define things at the high level now. So if you look at functions of this type, so for functions of this type, we say n is the frequency. And by frequency, we mean like how rapidly the function oscillates. So what does that mean? Let's look at that. Let's look at an example over here. If you look at cosine 2 pi x, this is the graph of it. And you notice that if you look between 0 and 1, for x between 0 and 1, we complete one oscillation. However, if you look at cosine 6 pi x, which is, by the way, cosine 2 pi times 3 times x, meaning the n is 3. In this case, what we see is that between 0 and 1, between x 0 and 1, we complete 3 oscillations. So it's cosine 6 pi x oscillates more rapidly. There's another term that we will need throughout the course, which is the term of amplitude. So let's talk about amplitude quickly. So the amplitude is going to be like if we have a constant multiplying, say, the cosine or the sine function, this constant is going to be called the amplitude. And what it does is that from the name, it changes the amplitude or the height of the function. So you can think of the amplitude as if it determines how strongly the oscillation is present. For example, if you were to plot 5 times cosine 2 pi x, you would, instead of having an amplitude of 1, you would have an amplitude of 5, meaning the peak is going to be at height 5, and so on. So roughly speaking, this is the concept of frequency and amplitude. Okay, so now let's get into some more formal stuff and discuss the motivation of this subject. So here's a quick motivation. So the idea is that there's a basic habit in mathematics, which is trying to understand a complicated object or function by expressing it in terms of simpler objects. For example, if you know a little bit of linear algebra, you would know that we usually speak of bases and we represent a vector, for example in Rn, as a linear combination of these basis elements. So so another example is, like, for example, polynomials. If you take a general polynomial p of x, if it's of, say, of degree n, then it can be written as an x to the n plus an minus 1 x to the n minus 1 plus the dot plus a0. Okay, and now suppose that you start with a general periodic function, a function that repeats. The question is, can we represent it in terms of these simpler objects, simpler functions that we know they oscillate? In other words, for periodic or repeating functions, can we represent them in terms of, quote-unquote, the natural elements? So the natural objects or elementary functions, they are like cosine, sine, cosine 2x, sine 2x, cosine 3x, etc. And maybe 1, the constant function 1, because remember here for polynomials we also use 1. And the question is, can we represent an arbitrary periodic function, a repeating function, in terms of these, depending on how frequent it oscillates? So this is the general question that we'd like to answer. Like, if I start with a general periodic function, say periodic, in other words, a repeating function with some period that we're gonna define things. We're gonna define things more formally soon. But let's say, suppose I start with a 2 pi periodic function, repeats every 2 pi. Can I represent it as a constant plus the sum and from n equals 1 to infinity of an cosine n x plus bn sine n x? So can I represent a function as a sum of these elementary elements in the same way we speak of bases? And for some reasons to be clear later, we usually normalize the first coefficient like this. So the question is this possible? And if it is possible, what are these ans and bn's? What are these coefficients? So a number of questions you can ask here. So some questions. What are the ans and the bn's? Another question. In what sense does this series converge? So you have an infinite series here. So in what sense does the series converge? And another question is, even if this series converges, does it equal f of x or not? So do we have the equality star? So let's call it star. Do we have this equality? Okay, so pretty much the entire first half of the course will try to answer these questions. Okay, so this is what we're hoping for, and for that we will begin by developing some theory. We're going to be defining things and proving some stuff about them, and then we'll see how things unfold naturally. Okay, so let's begin by recalling Euler's formula. So recall, as a basic thing to remember, if you've taken basic complex analysis, you would know that this is, or a basic, it could have been discussed in a calculus course as well. We have the identity e to the I n x. This is cosine n x plus I sine n x. So if I'm hoping for something like this, and I know that this is how e and cosine and sine relate, then the question of representing things in terms of sine and cosine can be symmetrically defined, or can be symmetrically reposed in terms of the elementary functions. So we can try to ask ourselves if we can represent things in terms of the elementary function. Let's say 1 e to the ix, e to the 2ix, and so on, and then e to the minus ix, e to the minus 2ix, and so on, where the constants here are the frequencies. And then we hope to represent f of x by a series of the form. So I'm going to be introducing some terminology now. F hat e to the I n x. So this is the hope, where n goes from minus infinity to infinity. So this is the hope. What do I mean by this? So this, you can think of it as the an and the bn's, but written in terms of f, because the an's and bn's better depend on f. Like, they can't be the same for a general f, right? So this is our hope, and instead of equality, let us normalize the notation. Let us normalize using the notation, the sim notation, to mean this f corresponds to this, but we don't know yet that there's an equality. And from now on, if we were able to do this, we shall refer to these constants as the Fourier coefficients. So these are the Fourier coefficients from now on, okay? And things will be defined soon. So before we define these coefficients, let's start with a 2 pi periodic function. So let's start with a 2 pi periodic function, and by that we mean f of x plus 2 pi equals to f of x for all x. So we're gonna call f 2 pi periodic if it repeats with every 2 pi, okay? Then observe that f is completely determined by its values on the interval minus pi. In other words, for those who know a little bit of algebra, we're gonna be studying what happens on the circle. So we're gonna be moding by 2 pi z, but if you don't know what that is, you can just forget about it. Okay, so it's enough to study the function here, because it's 2 pi periodic. It repeats every 2 pi. So the whole values on the real line are determined by those values that correspond to x's over here. So as long as x is here, I can map any x outside this interval there by periodicity, because the values repeat, right? Okay, so let us define the average. Let's define the average of f to be, you integrate between minus pi and pi, you integrate the function f of x, and then you divide by the length of the interval. So this is 1 over 2 pi. So this gives us an average of the function. It turns out that this is going to be related to the constant coefficient that we've seen in this expression here. But our purpose now, so let's call this goal 1. So our goal 1 is to define the ANs and the BNs. In other words, we'd like to find out what the FNs, f hat of n's are, the Fourier coefficients. We'd like to know what these things are. Okay, for that we need to introduce some terminologies and concepts, and we're going to begin with the concept of an inner product. So if we have two functions f and g, let's define the inner product of these to be 1 over 2 pi the integral from minus pi to pi of f of x g of x bar dx. So this is going to be called the inner product of f and g. So this is analogous with the inner product you've seen in linear algebra, right? So you define the inner product of two vectors to be the sum of uj vj bar, where by bar here we mean the complex conjugate. Like if we're working with functions f and g, and they are 2 pi periodic, we conjugate the value of g. Okay, so this is the inner product. From the inner product, we get a norm. So let's define a norm. So let's define the size of f, or the norm of f. And this is also called the L2 size or norm of f. Let's define this to be the norm sub 2. This is going to be 1 over 2 pi, the integral from minus pi to pi of f of x squared dx, and then we take square root. So in other words, what we've done is, observe that this is the same thing as taking the inner product of f with itself and then square rooting that. And that's because f times f bar, if we replace g by f, then f times f bar is the absolute value squared. Okay. So now we have some basic tools that we can play with. And let's prove our first theorem that will lead us to the definition of these objects. So let's prove our first theorem. So here's a theorem that we need. Let's call it theorem 1. And let's call this the orthogonality property. So this is called the orthogonality of the exponentials. Okay, so what does that mean? So this is what the theorem says. For integers m and n, we have this orthogonality property that the integral of e to the inx e to the imx conjugated dx is equal to 1 if n is equal to m, and 0 otherwise. In other words, if I take the inner product of these two functions, then it's gonna be like this. It's gonna be 1 if m is n itself, and if I take any two numbers, like if I take any two different numbers, like for example e to the 2ix and e to the 3ix, the inner product is 0 because 2 and 3 are different. E to the minus 2ix, e to the minus 2ix, since we have minus 2 and minus 2 the same, this is going to be 1. So this is what we're hoping for. Okay? So let's see how we prove this. Okay, so here's a proof. It's basically a basic calculation, but let's carry it out real quick. Alright, so let's begin by observing that e to the inx times e to the imx bar, this is the same as e to the inx, e to the conjugating this thing, it becomes minus imx, because it's just an imaginary thing, x is real here. So this is the conjugate of the complex number, which equals e to the, we can take a common I, and then n minus m, and then x. So this is what the integrand is. So let's see how we integrate it real quick. So the integral, let's call it I, or maybe we can just say this is einx, eimx. This equals the integral from minus pi to pi of e to the I n minus m x dx. Okay? Well, basic integration, basic calculus. This is 1 over 2 pi e to the I n minus mx over I n minus m. This is okay as long as n is not m, because if n is m, I cannot divide by 0 here. So this is, if n is not equal to m, this is okay. This integral is okay, okay? But then if you evaluate this, you see that this must be, if you take the difference of these two, this must be 0. And the reason is e to the I n minus m times pi, this equals minus 1 to the n minus m, because e to the I pi is minus 1. So this is, I'm justifying here why this is the case. And if you evaluate at the other endpoint, this is also the same thing. So this is also n minus m pi. You can check this, but the basic calculus, this is equal to 0. So whenever n is not equal to m, we have this. What if n is equal to m? Meaning if I'm inner producting the same thing, the same exponential thing, then this is 1 over 2 pi, the integral. If n equals m, then the integrand is e to the 0, and e to the 0 is 1, right? So this is 1 dx, and this is 1 over 2 pi times 2 pi, which is 1. Just carry out the integration. Okay, this proves our first theorem. And it says if you take two exponentials with different frequencies, then they must have a 0 inner product, and that's the orthogonality property. We call this orthogonality. Okay, let's keep going, and now we're ready to make the definition. So let's now define the Fourier coefficient. The idea, we're gonna see why this definition makes sense, but let's make this definition first. So let's define fn hat to be the inner product of f and e to the inx. In other words, we're gonna define fn hat, or f hat of n, to be 1 over 2 pi, the integral from minus pi to pi, of f of x, e to the minus inx dx. So this is the definition that we want to make. And from now on, whenever we write this thing, whenever we write f hat of n, this is the definition that should come to your mind, okay? This is the definition that we'll be talking about. And okay, so let's see, why does that make sense? Why does this definition make sense? Well, so this is the definition. But why? As a rough motivation, we're going to be seeing some more reasons later, but as a rough motivation, remember that our hope is to represent f by a series of the form f hat of n e to the inx, as n runs from minus infinity to infinity. So this is the hope. But if this is the hope, then if you think a little bit about it, you would say, well, if this were an equality, then if I inner product this sum, if I inner product this sum over here, this is rather informal, right? We're not justifying the analysis here. We're just motivating things. We're going to be justifying the analysis later. But informally, if I were to take the inner product of f, with e to the imx, then according to this definition, I should expect the answer to be f hat of m, right? But that is the case because informally, so this is informally, meaning I'm not justifying what's going on, but we're going to be justifying soon. Informally, we expect something like, we expect this to be something like f hat of n EINX, EIMX, like taking this constant out of the inner product and then summing individually. Then by the previous theorem, we know that this inner product over here, it's 0 for every n except when n is equal to m, right? It's 1. So this is 0 for all n's except when m is equal to when n is equal to m. But then this means that the only n that survives is the n that equals m, in which case we multiply this by 1, and otherwise we're multiplying it by 0, which gives us this f hat of m. Thus the definition f hat of m equal to f of x inner product EIMX at least makes sense informally, okay? So from now on, we're going to refer to the Fourier coefficient of f at n to be this thingy over here. All right. But before we go ahead and see an example, let's quickly, before we see an example, I guess, let's try to derive the a_n's and b_n's in terms of this. So next, let's derive an and bn that we saw in sums of the form. So in sums of the form, let's write it on a new line. The sum of an cosine and x plus bn sine and x. And then we had an a0 over 2. So this is it's from 1 to infinity. So this is the, we said that this is the alternative hope, I guess, because there's sort of this equivalence between cosine and sine. So let's see the how are the an's and the bn's related to the f hat of n. So we want to explain how we want to derive these an's in terms of f hat of n. So let's see how to do that. Well, what we're gonna do is we're gonna observe. So for that, let's observe that by definition this f hat of n is 1 over 2 pi, the integral from minus pi to pi of f of x e to the minus, don't forget the minus, I and x dx. And by Euler, we know that e to the, let's say, I times minus nx, this equals cosine minus nx plus I sine minus nx, which can be simplified to be cosine nx plus, rather, minus sine I sine nx, right? Just pulling the minus out. And let's plug here. Let's plug star. This leaves us with 1 over 2 pi, the integral from minus pi to pi of f of x cosine nx minus I sine nx dx. And let's further expand. So this is 1 over 2 pi, the integral from minus pi to pi. Let's expand this, cosine nx dx, and then minus, can pull the I out, so I over 2 pi, the integral from minus pi to pi, f of x sine nx dx. Okay. And based on this expansion, here's what we're going to define. We're going to define an to be 1 over pi, the integral from minus pi to pi of f of x cosine nx dx. And we're going to see why I'm ignoring the 2 here. And bn, we're going to define it to be 1 over pi, the integral from minus pi to pi, f of x sine nx dx. In other words, I'm defining things in an analogous way. We said that if we're expecting something like this, we're gonna define things, define the nth Fourier coefficient to be integration against this thing. So analogously, we're going to define the an to be integration against the cosine, and the bn to be integration against the sine. And matter of fact, this also follows from some orthogonality properties, but let's take these as definitions for now. And then the observation is that what happens is that if you look at it, f hat of n, this is going to be an minus I bn over 2. Okay? So if you think about it, f hat of n is going to be, this is an over 2, and this is I bn over 2 based on these definitions. And thus this is what f hat of n is. Similarly, if you replace n with minus n, you can see, so if you replace n with minus n, replacing n by minus n here doesn't change the cosine. Replacing n by minus n here flips the sign over here. So instead of a minus, it becomes a plus. So an plus I bn over 2. Alright, so this is the relation between f hat n and ans and bns. So the point of all this is to say that if we make these definitions, if we make definition 1, definition 2, and definition 3, if we make these three definitions, what we have is that if we're trying to explain that this thing is essentially the same as this thing, so this is what we're trying to explain over here. So we want to show why these two are the same, and it doesn't matter which one you work with. Well, with these definitions that we made, that becomes clear, because what I can do is I can take this term, I can take this sum, and combine the n term and the minus n term, meaning the every term with its negative correspondence. Then if you expand this thing, you will see that this is the same as cosine, an cosine nx plus bn sine nx. And you can see this, for example, by expanding this thing as cosine nx plus I sine nx, and this as cosine nx minus I sine nx, and plug things here and use these two as well and expand, for example, then you can see that we arrive at this thing. Okay? In other words, these two expressions are one and the same if you make these definitions. Of course, here we're doing things formally. We're not worrying about convergence and stuff. And then there's one thing that is left for us to do. This takes care of, so this infinite sum over here, you can think of it as a sum over the negative n's, so n less than or equal to minus 1, and then the sum over the positive n's, and then there's the zeroth term, the one corresponding to n equals 0. Okay, so we said that if we group the negative ones with the positive ones, we end up with exactly this one, as expected. And then there's one thing left here, which is the definition of A0. So for A0, what we're gonna do is we're gonna like compare the 0th term here and the 0th term here and make them equal. So we can define A0. So the 0th term here, so n equals 0 term. On the left side, this is f hat of 0 e to the 0. And on the right side, this is A0 over 2. So we're going to define A0, and this is e to the 0 is 1, so this is the same as f hat of 0. So we're going to define A0 to be 2 times f hat of 0. Okay, so all of this discussion is to introduce the definitions of the Fourier coefficients that make sense in our case. And these are the definitions that we're going to be working with. Okay, so we have the definition of f hat of n, and we have the right choice of definitions for a_n's and b_n's that make these two expressions one and the same, including this definition over here, right? So with these definitions, this expression over here, these two series at least at a formal level, these two are the same. Okay, so let's take an example. We've done a little bit too much theory now. So let's take an example. So let's look at, so here's an example, say example 1. So let's take the function f of x equal to cosine 3x. And cosine 3x. And let us ask ourselves the sort of a trivial or naive question. Can we represent this function in terms of simpler functions? It's rather funny to ask this question because it's already simple here. But let's see if we were to carry out these, if we were to carry out the steps of the calculation steps of finding the f hat n's or the a n's or the b n's, do we get the same thing as cosine 3x? In other words, we want to express f as a sum of f hat n e to the I n x as n runs from minus infinity to infinity, or in the alternative form, cosine nx plus bn sine nx, n equals 1 to infinity and a0 over 2. Okay, so let's do some quick calculations over here. Well, let's see. Let's try to calculate the f hat n. But before that, let's remember that cosine 3x, it's the real part of e to the 3ix. Because remember, maybe over here, e to the 3ix by Euler, this is cosine 3x plus I sine 3x. So cosine is the real part of this, but if you know a little bit of complex analysis, the real part is defined as the complex number plus its conjugate. So you conjugate this over 2. In other words, cosine can be written as e to the 3ix with a half plus a half e to the minus 3ix. So this is the representation of cosine that we expect to get. But let's see if we calculate the f hats, does this agree with the expected expression? Okay, so let's see. Well, f hat of n, so by definition, this is the integral from minus pi to pi of cosine 3x e to the minus I n x dx. So using this over here and putting things in, maybe taking the half out as well, So the half that time is 1 over 2 pi times the integral minus pi to pi. In this case, this is the f of x, by the way. So this becomes e to the 3ix, e to the minus 3ix times e to the minus inx. Here we're perhaps doing unnecessary calculation, but just to illustrate something. So this is half times 1 over 2 pi, parentheses, the integral from minus pi to pi of, let's see, so this is e to the, if we expand and take ix as common, this has become e to the I 3 minus nx plus dx plus the integral from minus pi to pi of e to the minus I times 3 plus nx dx. And we know from the previous proof, or you can do simple calculation here, that this integral over here, it's gonna be equal to 2 pi if n is 0, if n is 3, excuse me. If you put n equals 3 here, this is e to the 0, e to the 1, and the integral of 1 is 2 pi. And if you use any other n, so otherwise, if you use any other n, this will be 0 by the calculation we carried out in the orthogonality proof, right? Or you can do it easily here. The same thing happens here. This is going to be 2 pi only if and only if n is equal to minus 3, like you put this equal to 0, and it's going to be 0 otherwise. If you're not convinced, you can carry out the calculation. All right, but then this means that the only two terms that survives, so let's see, if n is 3, then I have 1 over 2 times 1 over 2 pi times 2 pi, so that's 1 over 2, and nothing from here, because n equals 3, we have 0 from here. Similarly, when n is minus 3, we have this term times the 2 pi, which is a half, and we have nothing from here because n equals minus 3 has a 0 value here. And this is going to be 0 otherwise. So otherwise, this is going to be 0. All right, so what does this mean? This means that the expected series of this shape, all of the n's have f hats equal to 0, except for n equals 3 and n equals minus 3. So except for n equals 3 and n equals minus 3, all the f hats are 0. And at 3 and minus 3, the value is half of f hat of n. So this is half e to the I 3x plus half e to the minus I 3x. But wait a sec, isn't this the same thing that we started with? Well, of course it is, and this is actually equal to cosine 3x. In other words, if you seek to represent a simple function in either form of these, in terms of simple functions, like in terms of this series that we are gonna later call, by the way, Fourier series, both of these are called like that, then if we seek to get such a representation, then we're gonna get nothing new because they're already simple. In other words, these coefficients, these detect the exact present frequencies. Like when we started with this function, it had a frequency 3x. It has a frequency 3, and the Fourier coefficient detected exactly that. It detected exactly that frequency and nothing else. Okay, so this was a first example. So let's take a little bit different example. So let's look at an example 2. Can we represent a function like f of x equal to x in terms of simpler function? But we need to be a little bit careful here. What do we mean by this? Because we agreed that we're going to ask this question only for periodic functions, meaning for functions that repeat. So how about we do this? Let's define this to be like that on minus pi pi. Okay, so let's define f of x to be x on minus pi pi and extend it periodically. I'm going to explain what I mean by this. So we're going to take f of x plus 2 pi to be f of x. In other words, geometrically, what I'm doing is that, so if this is pi, this is minus pi, say, then we're speaking of the line, so this is minus pi as well, this is pi. We're speaking of this line through the origin. Speaking of this line, and what we're gonna do is we're gonna take this line and repeat it. So next time at 2 pi we have the same repeated line. And so on. We're gonna repeat the line as well over here. The same line. So this is what we're doing here. This is the function defined everywhere, I guess. So for example, if you ask me what is f at I don't know 2.2 pi, I tell you I know the value between minus pi and pi for x for input between minus pi and pi. I know the value. It's going to be the input itself. But we also know that this is periodic, so we can bring everything back to minus pi pi. So this is the same thing as 2.2 pi minus 2 pi, because the value doesn't change if we add or subtract 2 pi, but by periodicity it repeats, right? So this is the same as f at 0.2 pi, and now this is between minus pi and pi. So so f of x is going to be x itself. By definition. So this is the value of this input, and so on and so forth. So the question is, can we represent this function, this periodic function, in terms of cosine and sine? In other words, if we try to approximate this function, can we approximate it by functions of this shape? Right? The sine and cosine have these shapes. Can we approximate this function by functions of this shape, or sums of functions of this shape? Let's see. Well, for that we need the Fourier coefficient, and then the hope is that we hope that we have some sort of relation or equality or approximation going on here between these two thingies. So this is what we're hoping eventually, but for now we're practicing finding these series for specific examples. Okay, so let's find this f hat of n. This is going to be by definition 1 over 2 pi, the integral between minus pi and pi of x. So it's going to be, let me write it one more time for you. This is f of x e to the minus I n x dx, but f of x is x on minus pi pi. So this is x e to the minus I n x dx. But then you could simply integrate this, e.g. you can introduce you can do it integrated by parts. For example, you can take u to be x and dv to be e to the minus I n x, however you want to do it. But if you do it by integration by parts, this is going to be x e to the minus I n x over minus I n between minus pi and pi, and then minus the integral between minus pi and pi of e to the minus I n x over minus I n dx. This is what we end up with. And then you can calculate this thing. If you evaluate and simplify, you should get something like 2 pi I times minus 1 to the n over n. And thus, we still need to evaluate this integral. However, so maybe let's put it here. Minus pi e to the minus I n x over minus I n dx. However, we know that this integral is 0. Maybe I missed a 2 pi somewhere here. Yeah, 1 over 2 pi. So this is the 1 over 2 pi that we missed. So before we continue, let's just to be fully careful. This is we're doing this calculation when n is not 0, right? For n not 0, this is okay because not 0 we're dividing by n, so we need to be careful. So when n is not 0, this is okay, and this is the answer, except that this can be simplified more. Exercise show that this integral is 0. We've done it multiple times now. It's simple calculus here. But this integral is 0, meaning the answer is these 2 pi's cancel, and the answer is I times minus 1 to the n over n. Okay, so this is f hat of n for n not equal to 0. Well, for n equal to 0, we go back here before we carry out the integration and put n equals 0, and we see that this becomes 1, and thus we're integrating x between minus pi and pi. So f hat of 0 is 1 over 2 pi, the integral between minus pi and pi of x dx, which is just the average of x, which is, you can calculate this. This is 1 over 2 pi times, well, we don't need to calculate it. X is odd, so this integral is 0, right? X is odd. We're integrating over a symmetric interval. All right, so this means that the series that we originally said it's like this, we can now replace these by the value that we found. And this is the case for every n that is not 0. So for every n between minus infinity and infinity, as long as it's not 0, we have this. And for 0, we saw that the value is 0, so there's 0 plus this. And this is supposed to represent x. This is going to be the Fourier series of x. So the hope is that eventually we're going to try to make sense of what this means, what this notation mean if we have equality, or if we ever have equality, or if we can approximate x by this thing. We're gonna discuss what this notation means, but this is what we have for now. Okay, so our next goal is to show, so moving on to a new topic, we're gonna be discussing the finite sums. Let's say we're going to be discussing finite trigonometric sums. And what do we mean by that? Well, what we're going to do is we're going to take this series, this Fourier series that we were discussing, but except of working with a series, we're going to work now with a finite version, a truncated version. We're going to truncate it at some n, at some level n, at some integer n, and stop there and not take any more coefficients. And we're gonna be seeing that these sums, they approximate. So these sums, we'll see that these sums, which we're gonna call Sn f of x, these sums approximate f of x in some sense that we're gonna discuss